Hello there, everyone. So this is the second video of section 1.4. So remember, last section we introduced this thing called the matrix vector product. And what I want to do in this video is relate it back to what we've been doing the first three sections. And we'll see that it relates in a way that actually doesn't introduce too much new material. It just winds up being a sort of new way to look at a system of equations. So I want to start off with theorem 3 plus. I say plus because I've added an extra sentence to what theorem point 3 is stated as in the book. This first sentence I added, I just wanted to remind us that, remember, if we've got this m by n matrix A and this vector x in Rn, then we defined the matrix vector product in the following way, where this is the sum of the columns of A times the corresponding indexed vector entry in X, right? So it's the first column of A times X1 plus the second column of A times X2, and so on. All right, so the bulk of theorem 3 says that the matrix equation AX equals B. And so remember from last video as well, AX is a vector in Rm, and so we're assuming that B is also a vector in Rm. And so what this matrix equation is, well, can we find, what this equality is asking if we've got this vector of variables x, is can we find a vector x with suitable variables that makes AX equal to B? Well, since I have this equality here, this matrix equation has the same solution as this vector equation. Remember, we had introduced this way of looking at a system of equations in section 1.3. And so this matrix equation has the same solution as this vector equation. And what was the punchline of section 1.3? Well, remember, the punchline of section 1.3 was that this vector equation has the same solution as the linear system, whose augmented matrix is just given by the matrix A, or I augment by adding one more column B at the end. And so if you remember going over how to find a solution to this vector equation, it turned out to be the exact same thing as finding a solution to just a standard system of equations. We just have to set up the correct augmented matrix, row reduce, and then look at what the corresponding solution would be. So really what this theorem is introducing, the only new thing it's introducing is yet another way of looking at a system of equations, where instead I'm going to represent this system as this matrix vector product equal to a vector B. And so in this equation, x represents my vector of variables. And so an interesting note, which is worth pointing out, we'll also sort of recall a definition from section 1.3, that if AX equals B has a solution, that is, I can find variables x1 through xn, or if you prefer, a vector x that makes this equation true. Well, remember that this equation here, if it has a solution, by definition, remember, means that B was a linear combination of the vectors a1, a2, up through an. Right? So remember, linear combination was just this definition that we introduced, where I've got scalar times vector plus scalar times vector equals vector. Right? And so a solution corresponds to finding scalars that equal x1 through xn that give me equality here. And so if AX equals B has a solution, then B is a linear combination of the columns of A. And so this statement isn't saying really anything new, because, right, the columns of A are given by these vectors, and so as we've already seen, if this has a solution, well, this has the same solution as this equation, and by definition, this equation says that B is a linear combination of these n vectors a1 through an. And so this is sort of just a fancy new way of saying exactly what this equation was already telling us. But sort of a trend, especially early on, is finding a lot of different ways to look at things, interpret things, and finding many different ways to say essentially the same thing. And so a reason for that, and I'm going to erase this now so we can go over an example, is that depending on the context you are trying to solve a problem in, sometimes being able to look at something in a different light will help you to solve one problem over another. So sometimes it's useful to look at a matrix equation. Sometimes it's useful to look at a vector equation. So we're just going to look at sort of a system, just an example where we sort of phrase this more as a matrix vector equation. So we want to find a solution, if one exists, and of course if one does not exist, then we should state that as well, to the equation ax equals b. And remember, this is just our new way of representing a system of equations. If A is the following matrix, and B is the following vector, so just for the fun of it, let's look at the system of equations that this matrix vector, that ax equals b corresponds to, right? So here, notice this vector x is this vector of three variables, x1, x2, x3. And so we want to find values for x1, x2, x3 that make this matrix vector equation ax equals b true. By theorem 3, this has the same solution to the following linear system, which I'll write down here. So you can sort of see how everything is lining up with this. The columns of this matrix A correspond to the coefficients attached to each of the variables. And B corresponds to my right-hand side of the equation, right? And so the solution to this system of equations should give me this vector, which makes this equation true. And so here x1 corresponds to x1 and the vector there, and x2 and x3 do as well. So we know how to find a solution to this system. Set up the augmented matrix. I will do it down here. Hopefully I have enough space for myself. 1, 2, 4, -2, 0, 1, 5, 2, and -2, -4, -3, 9. All right, so first thing I'm going to do, I want to start with this 1 and clear out all of the entries below. So I'm going to do 2 row 1 plus row 3, and this is going to replace row 3. So that gets me the following matrix. Next, I'm going to divide through in row 3 by 5. This is because I recognize that I want this position to be a pivot in my reduced row echelon matrix, or this position is going to be a pivot, right? Meaning it's going to correspond to a leading 1 in my reduced row echelon form matrix. And so generally, if I know this position is going to correspond to a leading 1, and all of the corresponding entries in the column are equal to, or are divisible by that same number, I tend to just divide through, right? And so what I tried to say, and I think fumbled a little bit there, was that because every entry in row 3 was divisible by 5, I just went ahead and divided by 5 and made my life easier moving forward. All right, so now I've got all of the entries below my leading ones cleared out. So now I want to start clearing out the entries above my leading ones. So I'm going to do negative 5 row 3 plus row 2 and replace row 2. In doing so, I get the following matrix. Now I'll do a couple row reduction steps at the same time just to wrap things up. So I want to clear out this 2 and this 4, right? So I'm going to do negative 4 row 3 plus row 1 to replace row 1, and I'm going to do negative 2 row 2 plus row 1 to replace row 1. And assuming I did everything correctly, hopefully, you should get the following reduced row echelon form matrix. I'll double check here. So negative 4 row 3 gets me negative 6. Yep. All right. So fun exercise if you want to sort of go back through the checklist. Convince yourself this is an RREF matrix. But remember, this corresponds to the solution to this system. x1 equals 0, x2 equals negative 3, and x3 equals 1, which should correspond to the solution vector x equals 0, negative 3, 1. And so what does that mean? That means that if I multiply A times this vector x, I should get this vector B. So let's verify that's true just to sort of convince ourselves that everything we're doing is valid. Plus we get to do the fun matrix vector multiplication dance. All right, so I'm going to take my, well, not the augmented matrix A. So I should be able to take my original matrix A, multiply it by this vector x, and get the vector B. So let's see what happens. All right, so we want to do this matrix times this vector. So take the first row, match it up with the vector. What do we get? We get 0 times 1 plus 2 times negative 3 is negative 6, plus 4 times 1 is 4. So far, so good. Second row, match it up with the vector. We get 0 times 0 plus negative 3 times 1 plus 5 times 1. And last row, match it up with the vector. We get negative 2 times 0 plus negative 4 times negative 3 plus negative 3 times 1. Adding up each of these entries, I do believe you get the vector B. And so notice, finding a solution to this matrix vector equation really is just equivalent to solving the corresponding system, which I had now erased, but I had up there. And so sure enough, this all works out the way it is supposed to work out. So we've got one more definition and one more theorem that I'll go over in this video. So I'll keep this up, I guess. So this is equal to -2, 2, 9. So this will be one of the more straightforward definitions, I think, that we introduced. But we say that a set of vectors in Rm spans Rm. And we'll say a set of vectors, I should name them. So we'll say a set of vectors v1 through vp spans Rm if the span of v1 through vp is equal to Rm. So, what does this mean? Well, remember that the span of a set of vectors is just all vectors which can be written as a linear combination of that set of vectors, right? Actually, we can see sort of a somewhat straightforward example here. So what we're saying here, right? So what this is that every linear combination of v1 through vp, or sorry, let me repeat myself. Any vector I take in Rm can be written as a linear combination of v1 through vp. So in a sense, remember I was describing the span as like the set of vectors that like these vectors can sort of get to, right? That like if I choose the right weights for each vector, I can get to this. I can get to any vector in Rm. So if the span of v1 through vp is equal to Rm, that means that every single vector in Rm can be written as a linear combination of these p vectors. And now that I've sufficiently confused you, let me give you an example which I think will make it a little more clear as to exactly what this is talking about. So this set 1, 0, 0, 1 spans R2. So why is this? Well, take any vector in R2. So let's say I have the vector 3, 2, which is a vector in R2, right? Because it's a vector of length 2. So I want to show that I can find a linear combination of 1, 0, and 0, 1 that equals the vector 3, 2. But with the two vectors I've chosen, it's not terribly hard to see what linear combination I need to choose, right? I just need to take 3 times 0, 1 plus 2 times, or 3 times 1, 0 plus 2 times 0, 1, and I get 3, 2. And so note, for any vector AB in R2, well, A times 1, 0 plus B times 0, 1 is equal to the vector AB. And so this here shows us that this set of vectors spans R2 because any vector I pick in R2 can be written as a linear combination of these two vectors. And so what this is saying, if we expand our dimensions or the lengths of our vectors out, any set of p vector, or any vector I pick in Rm can be written as a linear combination of these p vectors. And so if that's the case, we say that this vector set of vectors spans Rm. So we will use this definition in stating theorem 4, which we will conclude the video with. which will give us sort of a nice way to tie together a lot of the things we have learned so far. So if A is an m by n matrix, then the following statements are equivalent. And saying this means that if one of these statements is true, then they are all true. And if one of these statements is false, then they are all false. So first, for every vector in Rm, Ax equals b has a solution. So this means for every vector you find in Rm, the matrix vector equation Ax equals b has a solution. But remember, A times x equals b, right, is just another way of saying, well, if this has a solution, b is a linear combination of the columns of A, so each b in Rm can be written as a linear combination of the columns of A. But notice, if every single b in Rm can be written as a linear combination of the columns of A, well, the span of the columns of A is equal to Rm, so that would mean that the columns of A span Rm, right? So that is, you give me any vector of length m, I can find appropriate weights so that I can combine the columns of A under the given weights to give me the vector you chose in Rm. D, I won't talk about too much why D is also equivalent for now. We will see later why D is equivalent. But A has a pivot position in every row. So keep D in mind. We won't talk too much right now about why D is also equivalent to A through C, but we'll see later on, very, very interestingly, that it is. And so be warned here, each of these statements applies to A, not the augmented matrix A, not the augmented matrix where I add B on as a final column, right? So all of these four statements apply to the coefficient matrix, not the augmented matrix. And so that wraps up this video. I think I've got one more video planned for this section. It'll be a relatively short video compared to what we've done so far, where I'm just going to go through one sort of interesting example of a type of problem you might see moving forward.